Okay, good morning everyone. Can you all hear me okay? Hear me at the back? Good, thank you. So let me welcome you to this course, Differential Equations, in Part 1A Maths. It's wonderful to see so many faces. Such is my social life. I haven't actually been in a room with so many people for the last 18 months, so it really is nice to see people. Okay, so I should just introduce myself. My name's Anthony Challinor. I'm a professor in the Department of Applied Maths and Theoretical Physics, and also jointly with the Institute of Astronomy. And my research interests are basically in cosmology. So cosmologists try and understand the large-scale properties of our universe. So it's my very great pleasure to take you for this course on differential equations. Where we're going to basically look at lots of cool methods and some of the phenomenology of differential equations that crop up all over the quantitative sciences and in applied mathematics. Okay, so I hope you've all had a chance to sort of settle in over the last week or so. Cambridge is a really fabulous place to live and to work, and I hope you're sort of starting to feel at home here now. So I'm just going to begin with just a few administrative details. I did send an email out via Moodle encouraging you to watch an introductory video. Hopefully many of you have seen that. If not, please watch it as soon as you can. It provides both some of these admin details, but also some of the motivation for the course. And there's a little bit of sort of background mathematics on properties of limits that I won't cover in these in-person lectures, but it will be very useful for you to review some of that if you haven't already. Okay, as you know, there's 24 lectures, Monday, Wednesday, Friday at 11 here, and you're already here, so that's good. Just in terms of housekeeping, please set your phones to silent if you can. Okay, I've lost the screen, but that doesn't. Lectures will be recorded, and they'll be made available on Moodle shortly afterwards. They're not live streamed, though. I believe we have auto recording that starts at 5 past the hour and ends at 5:02, so I'll have to end abruptly then, or at least for the purpose of the recording. There are full lecture notes provided. The first couple of those is on Moodle already. If you take a look at those, you'll find that they have a bit more detail in them we'll actually cover in the lectures, and certainly everything there's more than I will actually write down during the lectures there. Some of it is just useful additional material, some provides a bit of background proof or something for some concepts. There's lots of space in the margins if you want to annotate those. So if any of you are I can see a few tablets around here. If anyone is used to writing on tablets, you might want to bring the notes on a tablet and just scribble in the margin rather than copying down everything I write. There's 4 example sheets for the course, and they're also linked from Moodle, and the first couple are up already. And finally, do feel free to ask questions. There's a few too many in the audience, really, to have much dialogue, I'm afraid, actually, during the lecture, but I'm always happy to discuss with you afterwards, or via email, or whatever mechanism you prefer. Okay, so I guess like the previous lecture, I'm going to use these visualizers, which I haven't used before, so you might have to bear with me, I'm afraid. But I'm going to write in 4 colors. Main text is going to be in black. I'll try and stick to this, but you'll have to bear with me. Displayed sort of mathematics, I'll try and write in blue. Things in green are comments or annotation, and examples I'll try and write in red. So that's what we're aiming for. The schedule for the course, the 24 lectures, they're split up roughly as advertised here. So we're going to begin in this lecture and the next 4 just with some recapping and extending some basic ideas in calculus. So some of this will be familiar to you, some of it won't, but it's a useful sort of leveling tool to get us all on the same page. And then we'll work through various systems of differential equations, starting with rather simple first-order linear equations, then moving on to look at some of the very rich phenomenology that arises in nonlinear differential equations, some work on higher-order differential equations, and finally some work on multivariate functions and what are called partial differential equations. Okay, this is very much an applied course. It is not a pure course. I am in no way a pure mathematician. In fact, as I said, I'm a cosmologist and astrophysicist. So this course is absolutely about methods and results and how to solve things rather than proof or existence. If that's not to your taste, don't worry, because you will get more than enough proof or existence and the like of many of the results in this course next term in the Analysis 1 course. Okay. I think that's it. So I'm going to switch to, or attempt to switch to these visualizers, and we can get started properly. So let's switch to dual projector. Okay. Let's just wait while the system starts up. Okay. Okay, so this is a course on differential equations, and of course, what are differential equations? Well, they're equations that involve derivatives of functions. So in this first topic, we're going to rehearse some basic ideas in calculus. So what is a derivative? Rules for taking derivatives. What's the inverse of a derivative? So an integral. And extend a little bit to look at how you take derivatives of functions with more than one variable, what are called partial derivatives. Okay, so our first topic, and the numbering in these handwritten notes, I will try and make coincide with the printed notes. So there should be a kind of one-to-one mapping between sections and section headings and things. So let's look at differentiation, first of all. So you all know what a derivative is. Intuitively, it's the slope of a graph at a point. It's telling you how rapidly the function changes as you change the argument. But let's just give the formal definition. Okay, so this is a definition, and the thing we're defining is the derivative of a function. Okay, so we're going to define the derivative of a function in the following way. So the derivative of some function f of x, where x is the argument. So the derivative with respect to the argument x so the derivative of function f of x with respect to the argument x is itself a function. So we're going to define it as a function. And that function is going to be a limit. So let's switch. I'm going to switch pens to blue. You obviously don't have to. So we're going to take the limit as h goes to 0 of, we're going to evaluate the function at some point x0 plus h. I'm then going to subtract the function evaluated at x0. I'm going to divide by h. And by definition, that is what we mean by the derivative of the function at the point x0. Okay, so we're taking a limit here as h goes to 0. And as I said, I'm not going to dwell in this course, at least in the in-person lectures, on what a limit is. Hopefully you have an intuitive notion that you're interested in how things behave here as we make h arbitrarily close to 0. But if you want some more sort of background material, on limits, either see the printed lecture notes, see the intro video, or if you can wait and you really want the details in all their gory, see Analysis 1 next term.
Sorry, could you write bigger, please?
I can try, yeah, sorry. Okay, so let's think about what this definition means pictorially, right? So if we have some function which we can draw just on some axes, so this is f of x, this is the argument x. We've got some point x naught, we've got some point x naught plus h. And then let's suppose our function is this blue curve like this. Then the value of the function at x naught is this black dot, and that's this term in this limit definition. The value of the function at x naught plus h is this right-hand black dot, and if I just join those by a straight line, then that straight line for finite h has a slope which is just, sorry, I will try and write bigger, is f at x naught plus h minus f at x naught divided by h. And the key point is as we take the limit as these points get closer and closer together, we're converging to basically the gradient or the slope of this curve at the point x naught. Okay, so not all functions have derivatives. So it's very important that for the derivative to exist, it doesn't matter exactly how you take this limit. And in particular, you could imagine, if you want the derivative at the point x naught, you could imagine the point x naught plus h being to the right, and then you move closer towards this point. Or you might take the limit where you start to the left, so h is negative, and move closer to this point. And for the derivative to exist and the function to be differentiable, you've got to be doing, those have to give the same result. Right? So for the derivative to exist, at some point x naught, we need the left and right-hand limits they must exist and be equal. Okay, so what that means is if I take the limit in the case where h is negative and approaches 0 from below, so we'll write that as limit h goes to 0 minus, and I do f x naught plus h minus f x naught over h. I need that to be the same as if I take the limit with bringing h to 0 from above, so we'll call that limit h goes to 0 plus f x naught plus h minus f x naught divided by h. And here, this is an example of a left-hand limit, and this is a right-hand limit. Okay, and this is actually quite restrictive. Functions basically have to be smooth enough for this property to be true. So this is actually quite a strong restriction on what we might call the smoothness of f of x. Okay, so let me give you an example of that. So actually, let me switch to Let me switch to this one. Okay, so let's consider the function f of x, which is just the absolute value of x. Okay, so what does this look like? Well, it's just it's this function. It's just the absolute value function. And let's just apply this definition here of a limit. And in particular, let's take the left and right-hand limits and see what we get. So if we do a left-hand limit, so we take the limit as h approaches 0 from below, then according to this, this definition of the derivative here and here, I'm supposed to evaluate the function f at where I'm trying to take the derivative, which here will be x equals 0, plus h, and h is negative here, so I'm going to be evaluating the function, say, here, and the function is going to be given by the absolute value of x at that point, so that's going to be the absolute value of h, and then I divide by h. But because h is negative, the absolute value is minus h, so this limit is minus 1. Whereas if I instead consider h positive, so I compare the function at this point to the function here, then I get plus 1. Okay, and they're not equal, right? So mod of x does not have a derivative at the point x equals 0. So we say it's not differentiable. So it's not differentiable at x equals 0, but it is everywhere else. Every other point is fine. Okay, let me just give you a little bit of notation. So far we've been writing derivatives in the form df dx. An alternative notation is to use this prime notation, so f prime of x, and sometimes, particularly when the argument is time, we use a dot, an over dot instead, so f dot. And they all mean exactly the same thing, just the derivative of the function with respect to the indicated argument. If you're interested in the history, this is actually due to Leibniz. This is Lagrange. And this is our very own Newton. Okay, so you really know you've made it in mathematics when people are still using your notations hundreds of years after you introduced it. Okay, and we'll sometimes extend this sort of prime notation. If you wanted to take the nth derivative of something, you'd have n primes, which rapidly gets very cumbersome. We'll sometimes use a sort of superscript notation. So the nth derivative we'll write as f superscript brackets n of x, and that just means take the derivative n times. Okay, so at this point, I want to introduce some notation that may or may not be familiar to you, which is what's called order of magnitude notation, or the idea of order parameters. So loosely, this is sometimes called sort of big O and little o notation. So as I said, these are sometimes called order parameters. Okay, so what this notation is, it's a way of trying to sort of formalize ways of comparing functions in the vicinity of some point. Informally we might say things like, oh, I have some function and near x equals 0, it goes to 0 faster than x. And, an example of such a function would be x squared, for example. Right? And if you imagine plotting those functions, x squared is clearly below x for small enough x. Right? And this big O and little o notation is just trying to formalize that. And it turns out to be very useful and very powerful when we try and prove some results in calculus, if we have this notation at hand. As I said, these are useful concepts. To give sort of comparative scalings. Of functions sufficiently close to some limiting point. Okay, so how do we define these things? Okay, so here's our definition, and this is big O and little o notation. So this is big O, and this is little o. And in typeset work, little o is generally not underlined. I will generally underline it here just to distinguish it in case it's not obvious which is bigger, my big O or my little o. Okay, so let's first of all define little o. Okay, so we say that if we have some function f of x, if that function is little o g of x as x approaches some point x naught, what that means is that if I take the limit as x approaches x naught of the ratio f of x to g of x, that limit has to be 0. Okay, so we'll explore a little bit more detail exactly what that means in a second. But let me just point out that this is sort of often written as f of x is little o of g of x. Okay. And if you see something like that written, what it means, if this applies as x goes to some point x0, it means that this limit of this ratio is 0 as x approaches x0. Okay, so informally what this means is if the limit f over g of x is going to 0, it means that f is much smaller than g in the vicinity of the point x0. Right, so the kind of informal definition, well, not definition, but the informal statement is that f of x is much smaller than g of x as x goes to x0. Okay, so that's the definition of little o. Big O is informally that f of x is bounded by g of x. So it's not necessarily much smaller, but it is bounded by it. So formally, the definition is that f of x is big O of g of x as x goes to x0 if there exists some delta which is bigger than 0 and some m which is bigger than 0, such that for all x basically within delta of the point x0, so for all x with the magnitude of x minus x0 being larger than 0, so I'm excluding the point x equals 0 from this definition, but less than the positive quantity delta, So if for all x within this range, the magnitude of f of x is less than or equal to the magnitude of g of x times this positive quantity m. So you have to be able to find a delta, positive delta, and a positive m, such that for x sort of within a range x naught around the point defined by this quantity delta, the function f is within m of g. And again, informally, this means that if you take, for example, f of x over g of x, this is now sort of bounded to be smaller than m as x approaches x0. And again, this is often written as f of x is big O g of x as x goes to x0. Okay, the equals sign here is actually a slight abuse of notation. The issue is that f of x is a function, but big O g of x is not a function. It's a whole class of functions. And the way you should really interpret this statement is that, you know, effectively f and g of x are, well, f of x is a function, whereas g of x is a sort of, well, it's some other function, but big O of g of x is a whole class of functions that satisfy this limit sort of definition that we wrote down here. So there's a kind of mild abuse of notation here. Okay, so we've defined things about the point x0, but we can easily extend it to behavior at infinity, and we often want to do that. We want to compare how functions approach, as the argument gets extremely large. So the extension to infinity is very similar. So we can extend behavior at infinity in the following way. So, you know, f of x is, say, for example, big O g of x as x tends to infinity if, and it's then very similar to this definition here, so there has to exist some x greater than 0 and some m greater than 0, and now such that for all x bigger than capital X, so that's replacing this sort of neighbourhood here about x0 just by now points all arguments x larger than some capital X. So for all values of x, we want the magnitude of f of x to be less than or equal to magnitude g of x times m. Okay, let's just note a few properties of these notations. So first of all, if we have f of x being little o g of x, then that says that, you know, the limit, let's say this is at the point x0, then as I approach x0, f of x is much smaller than g of x informally. So it's certainly true that f of x is bounded by g of x, right, because it's much smaller than it. So this necessarily implies that f of x is also big O of g of x, because, as I said, f will be bounded by g. But the inference is not true the other way around, right? We can have functions that are, f of x can be of order big O of g of x, but not be little o of g of x. So let's just look at an example of that case. So let's take the function f of x is 2x. Okay, very simple function. just a linear dependence. So clearly, given our definitions, f of x is big O x, say as x goes to 0, just because f of x, which is 2x, is certainly bounded by the function x, i.e. it satisfies this definition with m equals 2. But f of x is not little o g of x as x goes to 0, because, and if I take the limit as x goes to 0 of f of x, that's 2x, divided by x, that's the thing we wanted to compare it to, then this is 2, and that's not equal to 0. And sorry, I should have said here, this g of x, that should have been an x. I'm saying f of x is not little o of x. Okay, let's just look at another example. So let's look at the function x squared plus x. And let's think about the behavior as x goes to infinity in this case. So my claim is that x squared plus x as x goes to infinity is big O x squared. Okay, why is that? Well, if we consider all values of x greater than 1, then if I look at the magnitude of x squared plus x, that's necessarily less than twice the magnitude of x squared when x is bigger than 1. And that's exactly the form of this, what we mean for f of x to be big O of g of x. So this statement is true, and the sort of bounding value here could be 2 or anything larger. Okay, so that just demonstrates the truth of this statement here. And this idea extends. So here we had x squared plus x, but you could imagine something more complicated. So say I had some an x to the n, an minus 1, x to the n minus 1, all the way up to just a constant term a naught. Then as x goes to infinity, provided this first term, an, is non-zero, this is just going to be of order, so big O of x to the n. When an is not equal to 0. Okay, and a final example, let's just think about the function sine 2x as x goes to 0, and this is big O of x. And the reason for that is just that if you think about the sort of Taylor series of sine 2x, around x equals 0, that looks like 2x. For small enough x. And that means that sine 2x is going to be bounded by x, so it's big O of x. Okay, so the key reason we're actually introducing these order parameters here is because, as I said, we want to use them to prove various things in calculus. So let's just see how that works. My claim is that these order parameters are particularly useful to classify remainder terms before taking limits So what do I mean by that? Well, let's consider the construct that appears when we're taking the derivative of f of x at the point x0. So we have the difference of the function, and then we divide it by h. So we can ask ourselves, what is this thing for finite h? What is it in terms of the derivative of f at x0? And it's going to be h times the derivative of f at x0 plus some remainder term. And my claim is that remainder term is little o of h. So it goes to 0 faster than h as h goes to 0. So if we just imagine dividing that statement that I've just said now, divide it by h, and just rearrange things, we have that df dx at x0 is the difference of the function divided by h, and then plus a remainder term divided by h. And my claim is that that remainder term is of order, it's little o of h, as h tends to 0. And it's very easy to show that this has to be true, because if I now take the limit of both sides as h goes to 0, well, the left-hand side is just df dx, so its limit is df dx at that point. The limit of this term is, by definition, the derivative. So whatever this kind of remainder term divided by h is, its limit as h goes to 0 has to be 0. So it must go, because we're dividing by h, it must go to 0 faster than h for the limit to vanish. So it must be little o of h. So the limit of the remainder term is 0, just by the definition of the derivative. And in particular, then, it follows that the following very useful result, that if I just rearrange this now, if I evaluate the function at the point x0 plus h, then that will be the value of the function at x0 plus h times the derivative of the function at x0 plus some remainder term, and that remainder term will be little o of h. And of course, this is just like the first, this is like the first couple of terms in the Taylor series of this quantity f x0 plus h. And this is just quantifying the remainder if you truncate that at a finite number of terms. Okay, and again, just in pictures, if this is x, f of x, here's my function, f of x, and if I take some point x0 and then some other point h away from it, if you think about what these two terms are, this is basically just constructing the tangent line to the curve at the point x0. So this curve I've just written, this line, is f of x0 plus x minus x0 times the derivative of f at x0. And this result just quantifies the size of the remainder, so the difference between the value of the tangent line at the point x0 plus h and the value of the function there. And that is order little h. Okay, so we're going to move on now to look at some basic rules which will be very familiar to you for taking derivatives of functions. And we're going to start with the chain rule. So the chain rule is useful when you're trying to take the derivative of a function of a function. Right, so you're trying to take the derivative of a function of a function. Okay, so let's just state formally what the chain rule is. Let's state this as a theorem. So given f of x, let's think of this function as being composed in the following way. So we have some function, capital F, and then that has some argument, and we take the argument to be some function g of x. And that defines some new function, little f of x. Okay, so given this situation, the chain rule tells us that the derivative of f with respect to x is just given by the derivative of the function capital F with respect to its argument. We'll call that f prime. And then evaluated at g of x times the derivative of g with respect to x. And this first term is sometimes written, you can think of that as kind of being df dg, so the derivative of f with respect to its argument, and then evaluated at g times dg dx. So this term here is this is the derivative of f with respect to its argument evaluated at g of x. Okay, so you'll all be super familiar with this, but let me just give you a quick example. So if we wanted to take the derivative of, say, the function sine of x squared plus x minus 2, then here our big F function is sine of something, and our little g is this argument x squared plus x minus 2. So the derivative of sine is cosine, and so I have cosine for the argument x squared plus x minus 2. And then I have to multiply by the derivative of that argument with respect to x. So that's just the derivative of x squared plus x minus 2 with respect to x. So that's 2x plus 1. So this term here is my f prime g of x, and this term is my dg dx. Okay, I'm not going to prove the chain rule here. If you're interested in the details, see the printed lecture notes, well, the typeset lecture notes. It's actually quite a nice example of using this big O and little o notation to prove this result. Okay, the next rule is just the product rule, which again you'll be familiar with. So again, let's just state this as a theorem, the product rule. So this says that given two functions, u, x, and v of x, if I take their product, so I define a new function f of x, which is u of x times v of x, then the derivative of f is v times the derivative of u plus u times the derivative of v. And if you want to prove this, it's actually left as an exercise on example sheet 1. Okay, so that's where you've got a product of two functions. You've probably also met the quotient rule when you've got a ratio of two functions, or a quotient of them. And that's just a special case of the product rule where you take v to 1 over v. So, for example, d by dx of u divided by v. If we just use the product rule and apply it to functions u and then 1 over v, this first term, we're going to have a 1 over v du dx, and then we're going to have a u times the derivative of 1 over v. And I can evaluate this term d by dx of 1 over v just using the chain rule to get u prime v, and then minus v prime u over v squared. And if you just neaten that up by multiplying this term on top and bottom by v, you'll get the familiar form of the quotient rule. Okay, so the product rule applies to the first derivative of a function, and what we'll do at the start of next time is look at what happens if you want to take multiple derivatives of a product, and that will lead to something called Leibniz's rule. But we have to leave it there because I'm probably going to get cut off the recording in 1 second, but thanks very much for listening, and have a good weekend, and I'll see you next Monday.